Dear students, I am Dr. K.M.Kathiresan, Director, Center for Graph Theory, Ayya Nadar Janaki Ammal College, Sivakasi. To study connected spaces and compact spaces, we want some basic concepts in topology. Let us discuss the needed basic concepts in topology one by one. The first basic concept is open sets and closed sets. If tau is a topology on X, then the ordered pair X comma tau is called a topological space, and the elements of tau are called open sets. So if A belongs to tau, then we say that A is open. On the other hand, if the complement of A belongs to tau, that is, if the complement of the set A is open, then we say that A is closed. So the definition for a closed set is its complement is open. For example, consider the set X is equal to 1, 2, 3, 4, and this tau is equal to pi X singleton 1, 1, 2, 1, 2, 3 is clearly topology on X. In this topological space, we see that 1, 2 is an open set because 1, 2 is a member of this tau. So it is an open set. Now consider the set singleton 4. The complement of singleton 4 is 1, 2, 3. And this 1, 2, 3 is an open set. So the complement of singleton 4 is open. Therefore, singleton 4 is a closed set. So in this way, we define open sets and closed sets. Now let us define the interior of a set. We consider a set A of a topological space X. The first question is, does there exist an open set contained in A? Yes. We can find at least one open set contained in A, namely empty set. So empty set is at least an open set contained in A. There may be several open sets contained in A. We find the union of all such open sets. That set is denoted by interior of A. So interior of A is the union of all open sets contained in A. Since it is the union of certain open sets, it is also an open set. Since the considered open sets are contained in A, the union is also contained in A. So the interior of A is an open set contained in A. Since it is the union of open sets, it is the largest open set contained in A. So equivalently, interior of A is the largest open set contained in A. For example, consider this topological space X comma tau. In this topological space, state A is equal to B, C, D and B is equal to B comma C. Let us find the interior of A. To find interior of A, we collect open sets which are contained in A. The first open set contained in A is empty set. Empty set is an open set contained in A. Then X is open but is not contained in A. Singleton A is an open set but is not contained in this set A. CD, it is an open set and this set is contained in A. So we can consider that C comma D. ACD, even though it is an open set, it is not contained in A. Similarly, ACDE is not contained in A. So there are two open sets, empty set and C comma D, which are open and contained in A. Therefore, interior of A is the union of these two open sets, C comma D. In this way, we find the interior of A. Now, what about interior of B? As usual, empty set is an open set contained in B. X is open but not contained in B. Singleton A, even though it is open, it is not contained in B. C comma D, not contained in B. ACD, which is not contained in B. And ACDE, which is not contained in B. So in this case, empty set is the only open set contained in B. Therefore, interior of B is equal to empty set. So in this way, we find the interior of a set. Now let us define the closure of a set. We consider a subset A of a topological space X. Here we find the closed sets containing A. Does there exist a closed set containing A? Yes. At least the whole set X is a closed set containing A. Similarly, we find all closed sets containing A. Then we find the intersection of all such closed sets containing A. That set is called the closure of A, and it is denoted by A bar or CL of A. So, the intersection of all closed sets containing A. Since it is the intersection of closed sets, it is also a closed set. Since each closed set considered here are sets containing A. Therefore, the intersection is also a set containing A. So, A bar is a set containing A. As it is the intersection of certain closed sets, it is the smallest. So, A bar is the smallest closed set containing A. So, equivalently, closure of a set is the smallest closed set containing A. For example, consider X is equal to A, B, C, D, E, and this tau is a topology on X. Take A is equal to singleton D. Let us find the closure of the set singleton D. To find the closure of the set A, we find first we list out all closed sets, then we list out all closed sets containing A. Here the closed sets are, in this topological space, the closed sets are X, that is complement of pi, that is X, and the complement of X is empty, complement of A is B, C, D, E. So in this way, we find the closed sets of the topological space. Now, among these closed sets, which closed sets are containing singleton D? X is a closed set containing D. So we can consider this X. The empty set is a closed set, but it does not contain A. B, C, D, E, it is a closed set containing A. ABE is a closed set, but does not contain A. BE does not contain A. And singleton B does not contain A. So the only closed sets containing A are X and the set B, C, D, E. So we find the intersection of two closed sets. The answer is B, C, D, E. So B, C, D, E is the closure of the set A. Now what about the closure of the set B, where the elements of B are A and C? Now, X is a closed set containing B, and the second closed set is empty. Empty set does not contain B. BCDE does not contain B. ABE does not contain B. BE does not contain B. Singleton B does not contain the set A, C. So the only closed set containing B is X alone. Therefore, closure of B is capital X itself. In this way, we find the closure of a set. For example, consider this topological space X. Here X is a topological space, and A is a subset. Interior of A is the largest open set contained in A. So interior of A is always contained in A. And A closure is the smallest closed set contained in A. So here the triangle is the closure of the set A. So A bar is a superset of A. So interior of A is contained in A is contained in A closure. So A lies between interior of A and the closure of the set. Now let us define the neighborhood. If U is an open set containing the point X, then U is called a neighborhood of X. So if you want to check whether a set is a neighborhood of X, first check whether it is open. Then check whether that set contains X. Then we can say that U is a neighborhood of X. For example, consider this topological space. In this topological space, consider this ACD. ACD is a member of tau, so it is an open set, and it contains the element C. Therefore, ACD is a neighborhood of C. Now what about ABC? ABC is not a neighborhood, even though ABC contains the point C, this ABC is not a member of tau. So it is not an open set, therefore it is not a neighborhood of C. What about the set ACD? ACD is also not a neighborhood of B, because even though ACD is an open set, it does not contain the point B. Therefore ACD is not a neighborhood of B. So if you want to show that A is a neighborhood of a point Z, first check whether Z belongs to A, and then check whether A is open. If it is so, then you can say that A is a neighborhood of that point. Now let us define the limit point of a set. Suppose A is a subset of a topological space X, and we consider a point X in X. This X is not necessarily a point of A, it is an arbitrary point in X. We say that this X is a limit point of A if every neighborhood of X intercepts A in some point other than X itself. So the first point is every neighborhood of X must intercept the set A. Not only that, it must intercept in some point other than X itself. Then we say that X is a limit point. And the set of all such limit points is denoted by A dash. For example, consider this topological space. X is equal to ABCDE, and this tau is a topology on X. Here we consider A is equal to AC. Now, what are the limit points of A? Let us start from the first point A. Here we say that singleton A is a neighborhood. Singleton A is a neighborhood of A. And it intercepts capital A. Singleton A intercepts capital A. Then immediately don't say that A is a limit point of A, because this neighborhood singleton A intercepts A, but it must intercept A in some point other than A. Therefore, this A is not a limit point of A. Then what about B? The neighborhoods of B are capital X is a neighborhood, and then capital X is the only neighborhood. Okay? Capital X is the only neighborhood of B, and that capital X intercepts A in some point other than B. Of course, X intercepts A in A, also X intercepts A in the point C also. So B is a limit point of A. So we can take B as a point in A dash. Then what about C? Again, we say that C comma D is a neighborhood. C comma D is a neighborhood, ACD is a neighborhood, ACDE is a neighborhood, and X is also a neighborhood of C. In particular, the C comma D is a neighborhood of C. And this set intercept capital A, of course. But C comma D intercepts A comma C only at the point C. But we want some other point other than C. So this C comma D, even though this neighborhood C comma D intercepts A, in the intersection we can't be able to find a point other than C. Therefore, this C is not a limit point of A. Now what about D? The neighborhoods of D are capital X, CD is another neighborhood, ACD another neighborhood, ACDE another neighborhood of D. And this CD intercepts A in the point other than C, namely, yes, CD is a neighborhood of D which intercepts A in the point C other than D. So similarly, ACD intercepts A in some point other than D. ACDE intercepts capital A in some point other than D. Therefore, D is a limit point. What about E? In this way, you won't say that E is also a limit point. So the limit points of A dash are B, comma, D, comma, E. So A dash is B, D, E. In this way, we find the limit points of a set. For example, consider this example. Here, this neighborhood, the neighborhood of X does not intercept A. Therefore, X is not a limit point. And Z is a point of A, and this neighborhood, this particular neighborhood, intersects A in some point. But in this intersection, Z is the only common point. So in this intersection, you are unable to find another point except this Z. Therefore, this Z is not a limit point of this A. What about Y? Here, a particular neighborhood of Y intersects A. So immediately don't say that Y is a limit point of A. If all the neighborhoods of Y intersect A in this way, then you can say that Y is a limit point of A. Now let us define a continuous function. F is a function from one topological space into another topological space. Tau n is a topology on X and tau 2 is a topology on Y. We say that F is continuous if for each open subset V of Y, the set F inverse of V is an open subset of X. So we take an arbitrary open set in Y, then find its inverse image. If the inverse image of that open set is also open in X, then we say that F is continuous. So if V belongs to tau 1, then F inverse of V belongs to tau 2, we say that F is a continuous function. That is, inverse image of open set is open. A function is continuous if inverse image of open set is open. For example, consider this topological space X. X is a set and tau X is the topology on X. Y is another set and tau Y is a topology on Y. Define a function F from X to Y by F of A is equal to Y, F of B is equal to Z, F of C is equal to W, F of D is equal to Z. Let us check whether F is a continuous function or not. In Y, we consider all open sets. For each open set, we check whether the inverse image is open or not. The first open set in Y is empty set. So first we find inverse image of F inverse of Y. F inverse of Y is always pi, and this pi is open in the first topological space X. Then the second open set in the Y is Y. So let us find F inverse of Y. In all cases, F inverse of Y equal to X, and X is open in the first topological space X. Okay, then we consider the third open set, singleton X in tau Y. F inverse of singleton X equal to, that is, for which point the image of X. There is no point in X whose image is X. Therefore, F inverse of X is empty set, and empty set is open in X. Then the next open set is singleton Y. Let us find F inverse of singleton Y. F inverse of singleton Y. That means the set of all points in X whose image is Y. Of course, the image of A is Y, so you can take A. Then image of B is Z, so don't take B. Image of C is W, so don't take C. Image of D is Z, so don't consider D. So F inverse of Y is singleton A, and singleton A is open in the first topological space. Then the next open set in Y is X comma Y. Let us find F inverse of X comma Y. F inverse of X comma Y is a set of all points in the topological space whose image is either X or Y. Here F of A is equal to Y, therefore you can consider A. Here F of B is equal to Z, so don't consider the point B. F of C is equal to W, F of D is equal to Z. We want to find elements in X whose image is X or Y. So A is the only point whose image is Y. Therefore, F inverse of X comma Y is equal to singleton A, and this singleton A is open in the first topological space. And then the last open set in the second topological space is Y is a W. So let us find F inverse of Y is a W. Y is a W is the set of all elements in X whose image is either Y or Z or W. This A goes to Y, so you can consider A, and this B goes to Z. Z is a point here, so you can consider B. Then C goes to W. C goes to W, so you can consider C. And D goes to Z. This is Z. So you can consider D also. Therefore, F inverse of Y is a W is A, B, C, D. And here we see that the inverse image of all the open sets are are open in the first topological space. Therefore, your function f is a continuous function from x to y. Now let us find a function which is not a continuous function. Now take the same topological spaces x and y. Define a function g from x to y by g of a is equal to x, g of b is equal to x, g of c is equal to z, and g of d is equal to w. Let us check whether the inverse image of every open set in y is open in x. In particular, consider this open set y is a w in y. Now what is G inverse of y is a w? G inverse of y is a w is the set of all elements in x whose image is either y or z or w. G of a is equal to x, and x is not a point in y is a w, so don't consider a. G of b is equal to x, and x is not a point in y. X is not a point in y is a w, so don't consider b. Then g of c is equal to z, and this z is a point in the set, so you can take c. The image of c is z, so you can consider c. And the image of d is w. W is a point in the set, therefore you can take d. So there are only two elements in x whose image is either y or z or w. The elements are c and d. And here we see that even though y z w is open in y, its inverse image g, d is not open in x. It is not a member of x. Therefore, this function g is not continuous. Now we want some more results to study connectedness and compactness. The first one is a subset A of a topological space is, suppose A is a subset of the topological space X. Then we want to check whether a point X belongs to A bar or not. There is a necessary and sufficient condition to verify whether X belongs to A bar or not. X belongs to A bar if and only if every neighborhood of X intersects A. And note that to show that X belongs to A bar, it is enough to show that every neighborhood of X intersects A in some point. It not necessary, you need not find some point other than X. If it intersects the set A, that is enough. So this is the necessary and sufficient condition for X belongs to A bar. Another result is, if you find A dash, then the union of A and A dash, A union A dash, coincides with A bar. This is another method of finding the closure of the set. To find the closure of the set, just we find the set of all limit points, then we adjoin all the limit points with A. The resulting set is the closure of the set. Now, based on this discussion, you may do the following two assignments. Take any set with the 6 elements, form a non-trivial topology on X, and consider two different subsets A and B in X. Take your own sets A and B, and for A and B find interior of A, interior of B, closure of A, closure of B, and the limit points of A and the limit points of B. Another assignment problem is, take two finite topological spaces X and Y and define your own function f from X to Y. We first construct the function in such a way that the function is continuous, and then construct another function from X to Y which is not continuous. So in this presentation, we have studied how to find the interior of a set, closure of a set, how to find the limit points, and how to check whether the given function is continuous or not. Thank you very much.